Okay, so this is about diagonalization, which is a technique that can be used to find the eigenvalues of some matrices. Um, the first thing we need to do is establish what are called similar matrices. Okay, a similar matrices, I have to start with something that is n by n, and another matrix P that is also n by n invertible. Okay, so invertible, non-singular, right? And then what we do here is we say that A prime is equal to P inverse AP. If I can do this, then we say that A prime and A are similar. So if there is some matrix P that I can do this with, that I can multiply one side by the inverse and the other side by P, then we say that A prime and A are similar, and we write that A prime is similar to A. Okay, so this leads me to a second idea, which are called diagonalizable matrices. Okay, so a diagonalizable matrix is a matrix in M n by n such that there is a diagonal matrix D where A is similar to D. Okay, and this is useful, okay, because the diagonal matrix, it's really easy to find the eigenvalues of, because the eigenvalues would be the values along the diagonal of this. So this leads us to our first theorem. Our theorem states that if A is similar to B, then A and B have the same eigenvalues. Okay, so proving this is actually pretty straightforward. We're going to choose, we're going to choose some P, which is n by n invertible, such that B is equal to P inverse AP. Okay, so it suffices to show here that the characteristic polynomial for B, lambda I minus B, is equal to the characteristic polynomial for A. If these two characteristic polynomials are equal, then their eigenvalues, the eigenvalues of B, have to equal the eigenvalues of A. All right, so let's start off with the characteristic polynomial of B. All right, so if I do that, I can replace the B with P inverse AP. Okay, so that's like the expected first move here. And then we have to be a little bit clever here. So what we're going to do is on this part here is we're going to surround this I with P inverse IP minus P inverse AP. Okay, so that's kind of easy. Since this is a scalar, it can move around. So I can go P inverse lambda IP minus P inverse AP, which now becomes, well, if I pull the P inverse from the left, so that's going to give me lambda I minus A, and the P from the right of both terms, so kind of reverse distribution here, factoring them out. We can get that. And then recall that the determinant of a product is equal to the product of the determinants, which now just made all of these things scalars, so I can swap them around by the commutative property. So that's going to give me P inverse times P times lambda I minus A. And at this point, it's just kind of follow your nose. The determinant of P inverse P, determinant of lambda I minus A. This is the determinant of I times lambda I minus A. And the determinant of I is 1, so this is just lambda I minus A. And that's what we're trying to prove, is that the two characteristic polynomials, lambda I minus B, is equal to lambda I minus A. Okay, so let's work an example here. We're going to let A be the matrix 1, 0, 0, negative 1, 1, negative 1, negative 2, 4. And we're going to let P be the matrix 1, 0, 0, 1, 1, 1, 1, 1, 2. Okay, so if you use MATLAB or you work it by hand, you're going to get that P inverse is the matrix 1, 0, 0, negative 1, 2, negative 1, 0, negative 1, 1. And you could check this, that if I let D equal P inverse AP, I'm going to get a diagonal matrix, which is 1, 0, 0, 0, 2, 0, 0, 0, 3. So I now know that the eigenvalues of both D and A are lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3, because the values on the diagonal of a diagonal matrix are the eigenvalues of that matrix. Okay. This brings me to our next theorem. This theorem says that if A is an n by n matrix, then it is diagonalizable if and only if A has n linearly independent eigenvectors. Okay, so we're going to have to prove this. This is an if and only if, so we have to prove it in two directions. Okay, so we're going to start by going this direction, which means we're going to start with A is diagonalizable, which just means that there exists D such that D is equal to P inverse AP, and D is a diagonal matrix. So we're going to give D a little bit of flesh here. We're going to say that its diagonal is lambda 1, lambda 2, down to lambda n, and that everything else in this matrix are zeros, right? Okay, so this is a diagonal matrix. And we're going to say P has columns. P1, P2, out to Pn. Okay? And if we take P times D, we're going to end up doing this, and we're going to get columns where we have lambda 1, P1, lambda 2, P2, out to lambda n, Pn. Okay, so these are the columns of P times D. All right, so we want to consider also A times P, right? So if I take A times this P matrix with the P columns, right, then what we end up with is a matrix that has the columns AP1, AP2, out to APN. Okay, so note D is equal to P inverse AP, right? This we just showed that we're saying that PD, so this would imply that PD has to equal AP, which means that lambda 1 P1, lambda 2 P2, out to lambda n Pn, right, has to equal AP1, AP2, out to APN. Okay, So this means that the lambda 1 and the a, or the lambda 1 p, the lambda n pn's and the a pn's. So if we kind of think about this, each of these then has to be an eigenvalue, because this is equal to that, the lambda p is equal to the AP, so each of these has to be an eigenvector, okay? Corresponding to the eigenvalues lambda 1, lambda 2 to lambda n. All right, now how do I know that they're linearly independent? Well, they have to be linearly independent because this is the matrix P that has each of those eigenvectors, or each of those eigenvectors. How do I know that they're independent? Because P is invertible, which means that if P is invertible, its columns have to be linearly independent. So if I can diagonalize the matrix, then there has to be a set of linearly independent eigenvalues and a full set of them. All right, so we've proven this going to the right. Okay, so now we've got to make this theorem go the other way. So let's see. This means that I have to start off with P1, P2, out to Pn being a set of linearly independent eigenvectors for A, right? And this means that I also need the corresponding eigenvalues. We can call those lambda 1, lambda 2, out to lambda n, okay? So these are also going to be, the eigenvalues, right? All right, so what do we know? We know that API has to equal lambda I pi for all I from 1 to n, right? Okay, so this means that the matrix AP should be A times these P columns, P1, P2, out to Pn, right? Which we know also has to be lambda P1, lambda 1 P1, lambda 2 P2, out to lambda n Pn, because this is what we kind of showed in the first half there. All right, so if I look at that, that decomposes into P1, P2, out to Pn, times the diagonal matrix lambda 1, 0, lambda 2, 0, out to 0, out to lambda n, with a 0 here, zeros everywhere else, right? So this decomposes into columns and this, which means that this is P times my D matrix, which means AP is equal to PD, and this is going to give me that D is equal to P inverse AP, which means that A is diagonalizable. All right, so that's the second direction, and that means I have proven this theorem. I want to note that when you do this VDIG routine, what you're actually getting in the V matrix is the P that we've talked about here, the linear independent set of eigenvectors, and D is the diagonal matrix whenever A is diagonalizable. So that V and D will actually be the P and D that we're using in these proofs. Okay, so we have one last little theorem here. Okay, we've said that if it's diagonalizable, then I have a set of n linearly independent eigenvalue vectors. Okay, what we want to prove here is another condition for diagonalization, which is that if a matrix has n distinct eigenvalues, then it is diagonalizable. Okay, so we're actually going to do a proof by induction here. The one case is trivial. Okay, if I have a set of one eigenvectors, then that set must be linearly independent. Okay, so that helps me. So what we're going to do is we're going to let lambda 1, lambda 2, out to lambda n be a set of distinct eigenvalues. Okay, and these are going to correspond to the eigenvectors x1, x2, out to xn. Okay, so let's pick some eigen. So we're going to do this. We're going to let m be strictly less than n. Now, the only time that I cannot be strictly less than n is when n equals 1, and n equals 1 is a trivial case. It's already a diagonal matrix. It's, size 1, so that's doesn't matter. So if m is less than n, we're going to assume, so we're going to make an assumption here, that A has m linearly independent eigenvectors. Okay, so this is like the idea of an inductive proof, that I'm going to prove it for n equals 1, which is trivial. I'm going to assume it for m, and then I'm going to show that if it's true for m, it has to also be true for m plus 1, which means that it has to be true for every possible size. So this is an inductive proof. Okay, so I'm going to make this assumption that it has m, where m is less than n, linearly independent eigenvectors. Okay, so we're going to call them x1, x2, out to xm, right? So we're going to pick the next eigenvector, and we're going to let it be a linear combination of the others. So xm1 is going to be c1x1 plus c2x2 out to cmxm, right? Okay, so it's a linear combination of all the others. And this is going to be that there has to exist a ci that does not equal to 0. Okay? And I has to be somewhere between 1 and m. Okay, so the idea here is that I have this is going to be a linear combination of these, and one of these coefficients has to be non-zero. Okay, now because these are eigenvectors, I'm going to throw in a here. So we're going to let a xm plus 1 be a c1 x1 plus a c2 x2 out to a cm xm, right? Now, I'm also going to create the other way. I'm going to say that lambda m plus 1 xm plus 1 is the same as a lambda 1 c1 x1 plus lambda 2 c2 x2 out to lambda m cm x m. So I have both parts of the eigen equation, right? So if I do this, all right, so let's get rid of some stuff up here, right? All right, so let's delete that. All right, if I do this, I now can subtract these things and get the 0 vector, right? So the 0 vector is now c1 times lambda 1 minus lambda m plus 1, right? x1, right? So I've subtracted Oh, I'm missing a step here. Hold on. Let's go back a minute here. If these are the A's, right, then let's get down here. I can rewrite this sentence here as lambda m plus 1 x m plus 1 as lambda m plus 1 c1 x 1 plus lambda m plus 1 c2 x 2 out to lambda m plus 1 cm xm. All right, so why does that work? Because if this is a times this, and lambda m plus 1 is going to be an eigenvalue for this, right, then I can replace the a with the lambda m plus 1, which means that here what I'm doing is I'm basically saying I'm actually not looking at this. I'm looking at the equation above. I'm distributing both sides. There it is. I'm taking the left-hand side, multiplying by lambda m plus 1, taking the right-hand side, multiplying by lambda m plus 1. And the two key equations that I need here, so let's circle these before we keep going, are this one, which I get by multiplying this on both sides by lambda m plus 1, and this one that I got from exercising that if I multiply it through by a, I can multiply it through by the eigenvalues. Okay, so this one here and the one below it are the two key equations that are going to allow me to do what I'm doing up here. Because if I subtract these, right, so this is the same as this, so that's going to give me the 0 vector. I can pull a c1 out. Here I have lambda 1 minus lambda m plus 1 times x1. So then I can do that again, continuing going forward. c2 is lambda 1 minus lambda m plus 1 x2 out to cm. Right, and that's going to be lambda m minus lambda m plus 1 xm. Okay, so that equals the 0 vector. Okay, now, okay, so let's get rid of some of this down here. Okay, I'm going to delete that. Undo this. Okay, so we know that there has to be some value in here where lambda I does not equal lambda m plus 1, because otherwise this thing is going to equal 0, right? So in the end of the day here, because these things, x1, x2, xm, are linearly independent, right? There has to be one of these things where this combination is not equal. Okay, actually, I take this back. The reason why these things can't be equal is because that's how we declared it. At the very top of this, we had that the eigenvalues had to be distinct. So I'm assuming that if I have a matrix of size m plus 1, then I have to have m plus 1 distinct eigenvalues. That means that these things cannot be equal. If they're not equal, and these guys are linearly independent, then what I have to have is that C1, C2 out to Cn, all of these have to be equal, and in fact they all have to equal 0, which is a contradiction of what we said earlier, that you had to have at least one of these that was not equal to 0. Okay, so we've got our contradiction. So this means you cannot write xm plus 1 as a linear combination of x1 out to xm. If that's the case, then x1 through not xm, but xm plus 1 has to be linearly independent. Okay, so that's what we're trying to get at. And if I'm linearly independent and I have a full set of linearly independent eigenvectors, then by earlier theorem I am diagonalizable. Okay, so let's think through how this works one more time. All right, so the idea here is that if I have, I'm assuming that I have let's try this again. I'm assuming that if I have a matrix, a submatrix, a subset of eigenvectors that are size m, right, and m is less than n, then I'm making this assumption that those are going to be linearly independent. So I'm making an assumption that my matrix A has m linearly independent eigenvectors. Now, from there, I can wind my way through this to show that if I have n distinct eigenvalues, which is the key fact here, that this one has to be distinct, I can show that having m distinct or linearly independent eigenvectors will now force me to have m plus 1 of them. And I can keep doing that until I get all the way to n, regardless of what n is. So I start with 1, I show that m leads to m plus 1, and that will ultimately get me from 1 to n. Now, once I have n linearly independent eigenvectors, right, so what we've just shown is that having n distinct eigenvalues gets me n linearly independent eigenvectors, and by earlier theorem that shows me that matrix A has to be diagonalizable. Alright, so the proof for this is all in the notes. Make sure you take a look at it and see how the form works. But we'll be using this theorem and others in class today. Okay, thank you.